So we are back again with our online classes of AccentUs, and today we'll be doing current, electricity, and since you already know that this chapter you have done in your lower classes, but still we will first revise all the concepts. The things you have done in lower classes is already included in class 12 syllabus. So we have to actually know those things we did before again, so that we understand the things more better. Keep your classwork ready, as well as we have lots of circuit diagrams, lot of diagrams to draw. So keep your pencils and other geometrical boxes and everything in front of you. So let's start current electricity today. So before going into the actual thing of current electricity, let us understand that how current flows through a conductor. Okay, so here we'll look into the electron level. We know the metals, they have a large amount of electrons available for their conduction band. I mean, for this reason they can conduct electricity, or even the thermal properties are very much prominent in case of metals. And there are some. So let us consider a conductor which is cylindrical in shape, and there is a current flowing through it. You can understand, and you know that the conventional direction of current is opposite to the direction of electron flow. So we can imagine that this current is flowing because of lot of electrons are actually flowing opposite to it, and due to that reason the current is flowing, is having a cross sectional area A, and the length of the conductor is L. Okay, so this is what we have, and let's say that this conductor, it contains n number of electrons. This is number of electrons per unit volume. Okay, so n is the number of electrons per unit volume. So what is the total number of electrons? I mean, what is the total charge? You can say the electronic charge is E, which is mentioned here. So total number of electrons into electronic charge will give me the total amount of charge. So total charge, you can say that the total charge is total number of electrons, which is n per unit volume. So n into A into L is the total number of electrons, into E is the electronic charge. Very good. And now we want to know about the current, right? So current is Q by T. Alright? So current is Q by T, and from here we can replace the total amount of charge that we have already derived, and I is equal to NEAL by T, and L by T. You see, Vd is the drift velocity. Vd is the velocity of the electron through which it drifts. It drifts means electron actually doesn't flow from one point to another point. It actually pushes the next electron to carry the energy forward. So that's why we call it drift velocity. Alright, I'll come to more details about it right after this. So L by T will give me the drift velocity, because the electron is traveling this length and in time t, and that is the reason why the current is flowing. Alright, so we can understand that Vd is L by T. So finally we can have this expression. You can see this is very important expression for current electricity, that I is equal to NEA Vd. This is a very important expression. We should know this, and I will also ask you to know about the current density. Current density is I by A. So obviously current density, what I can say that J is equal to NEVD. Okay, so this is called the current density. Please write it down. Current density is amount of current per unit area is NEVD. A is getting cancelled. So current density is having this expression. Alright, now I'll move into more about this drift velocity and resistance and other things, and let us do that. So now we know about the relation between the current and drift velocity, that is I equals to NEVD. I didn't erase that, but now we have to know more about it. Okay, so we are thinking about a conductor where the current is flowing. Now my question is, why current is flowing? Current is flowing because there is a potential difference. Current flows because whenever there is a potential difference, then only the current flows. How we are keeping the potential difference? We are actually providing an electric field which is actually creating a potential, and then the current is flowing. So the main factor here is the electric field that we are applying across the conductor, which is initiating the current to flow, and which is also initiating the free electrons in the conduction band to drift in order to carry the amount of current corresponding to the applied electric field. Please remember this, applied electric field is important. Okay, so let us see. It will yield us to a lot of good results. You know, we can actually see how it happens, how it works. Okay, so let's try for this. What's the fact here? That we are applying an electric field. Current is flowing due to potential. Okay, so what is electric field? Electric field is potential gradient. Remember, the length of the conductor was L, so potential, if it is applied V, then electric field is V by L. Okay, so what is the amount of force that an electron will experience because of application of this electric field? The force will experience by electron is QE or EE, and that is EV by L. And from here we can actually calculate the acceleration of the electron that is gaining, and that is equal to EV by ml, where m or m suffix e also we can write, where it is the mass of electron. Okay, so keep it as an expression here. Now we'll think, and I must tell you a very interesting story here. What is the story? You know, in our school, when we go to school, nowadays we are not going, but anyways, when we used to go to school and when we'll be going to school again, then what we go to the school, we keep our bags in the classroom and we come back for the, you know, prayer, the assembly. So during the assembly, before it starts, what we see on the ground or in the hall, we see the students, they are scattered. Okay, so here also the electrons within the conductor, it has got plenty of electrons which can carry current, but they are scattered, they are moving in their own way, they are vibrating, they are moving, they are drifting, but their own way, they do not have any particular directional aspect. So same thing occurs in that particular hall or in that particular lawn or playground where lots of students gather for the morning assembly, and during that time the students, they are scattered, but once the bell rings, they all get aligned on their respective class lines, and then they start their prayers or then they start their assembly the same way. The electrons which were scattered within the conductor, now when we apply this electric field, then these electrons gain enough acceleration so that they actually get aligned and they finally get drifted in a particular linear direction so that the current flows. I equals to NEAVD. Okay, so this is the story. Just remember that initially the electrons were scattered, and if initially the electrons were scattered, then I can find out that U average, the initial velocity of electron, is actually, if there are n number of electrons, then it is like this. We can go on, and since these are all vectors, we can find the average, and this average is 0 because they are not directed, they are scattered, they are not showing any particular direction of motion or flow or drift. Okay, so this is final. So now we want to calculate the drift velocity, which is equal to U AV initial plus A into tau. Now what is tau? Tau is the average relaxation time from an electron getting aligned from a state of getting of a state of scattered. Okay, electrons were initially scattered, now they are aligned. So the time taken by individual electrons to get convert in this fashion is known as the average relaxation time, which is tau. Please remember this, average relaxation time or tau. Okay, and now we can actually find out the drift velocity now, because we have all the things together here. This is 0, so acceleration is this, so we can write EV by m suffix e into L. This is the acceleration into tau, this is the VD. Alright, now what is current? Current is NEAVD, so NE, that is E square, A NEA, this done, then VD, so capital V by ME into L. You see, we have an expression here, and we can say that this NE square A by MEL, This is a constant and it proves the Ohm's law. V is proportional to I. This is a constant, and this constant is what we call it resistance. So we can easily say V equals to IR. So we can easily say that resistance is equal to MEL by NE square into A. And from here you can actually see the laws of resistance. We can see here that R is directly proportional to L and inversely proportional to A, and thermal properties are also important here because I'm sorry, there was a tau. There was a tau here, and for that reason there will be a tau here. Okay, so even when we increase the temperature, the average relaxation time also increases, and which reduces the resistance. You see, from this expression we can tell a lot of things. We can even tell the justification of the phrase in Ohm's law. Temperature and other physical properties remaining constant, then only this law is valid. Okay, so you can understand that Ohm's law is proved, and even we have understood how we can calculate or how we can see the resistance, and even what are the factors that affects the resistance of a conductor. Okay, you can easily find out from here. The nature of the material actually denotes the number of electrons available per unit volume of that conductor. The area is here. Average relaxation time is related to the temperature part, because when we increase the temperature, the average relaxation time also increases, so the resistance decreases because it is inversely proportional. So this kind of question, it comes in the entrance also. So these concepts are important. In your textbook these are clearly mentioned. Please go through those things and please write all these things and remember these expressions because these are important for boards as well as for the entrance examination. You can see a lot of questions have come from this particular section. From using these concepts you have to answer. Okay, so here it is. Now we have concluded this. Now let us move to the next topic. So let us see how we can verify Ohm's law through a circuit. I have drawn the circuit diagram here. It's a simple one. We have one external resistance, we have one battery with certain potential, the marked EMF. We also have a rheostat, the variable resistance, in order to we can change the resistance, which is connected in series. And we have one ammeter and one voltmeter, which is connected in parallel across the external resistance, and the ammeter is connected in series with the battery. We also have a key. In order to insert the rheostat, we place a key there. So this is the circuit. You should draw this circuit in your classwork, and through this circuit we can actually verify the Ohm's law. Okay, this is important because until and unless these concepts are clear to you, you won't be able to understand the basic of current electricity. It is very important, I am telling you. So this is the arrangement, and what we do is we actually change this rheostat. We change the varying resistance, and we calculate, we see the reading in the ammeter and the voltmeter. Okay, do remember while drawing this circuit, these plus minus symbols are very important, because this will help you to know how voltmeter and ammeter is connected with their terminals in which side. Okay, so like in ammeter you can see that it is in the negative side with the battery, and in here it is also in the positive side with the battery. And remember one thing, that resistance, whenever you are connecting any resistance, it does not have any positive negative. Okay, it can be connected in any way you want. Resistance does not have any positive terminal or negative terminal, unlike the others do. Okay, so we have voltmeter and ammeter here, and we have this resistance. So we plot different potentials and we plot different current. One is recorded in the voltmeter, one is recorded in the ammeter with a varying resistance using a rheostat or a potential or the resistance box, whatever is available. And then we plot all these values and then we draw the graph. Okay, so ideally the graph should look like this. which is V versus I graph, and it will be a straight line according to Ohm's law, which is V proportional to I, so it will be a straight line passing through origin, and this slope definitely will give me the resistance. V by I, the slope, will give me the resistance of the particular the external resistance or whatever we are connecting. So this is fine. This we have understood, and these kind of graphs, they are called ohmic graphs. But practically what happens, you say in Ohm's law we already have this phrase that temperature and other physical properties remaining constant. But when current flows through a resistance, the temperature does not remain constant, because when the current is flowing through the circuit, due to the electron drift, due to the flow of electron and other things, the temperature increases within the conductor. You'll see that all the electrical appliances, they get heated up after a certain amount of use. So the temperature will change, and then when the temperature is changing, we should know that the resistance depends on a particular thing. The resistance at a particular temperature is equal to resistance at 0 degree C into 1 plus alpha into change in temperature into T, you can say, where alpha is called the temperature coefficient of resistance. That means it is actually, it shows that how resistance changes with the temperature. For a normal conductor, it is the expression RT equals to R naught into 1 plus alpha T. This is the variation which is given, with respect to temperature, how resistance varies. So here also the resistance varies, and definitely what will happen is that we won't get a curve like this. We'll get a curve which is something different, and that is called non-ohmic graph, which is the ideal situation. And for non-ohmic graph, we'll be getting a curve, not a straight line. And in that case, you'll choose certain points, and we calculate the change in potential as well as the change in current. So this will give me the change in potential, this will give me the change in current, and the resistance is given as like this. You see the difference between these two, the slope from these two different graphs are different. One is V by I directly because it was general ideal plotting of the graph, which is the ohmic graph, and this is called non-ohmic graph, where the temperature of the conductor will increase, correspondingly the resistance will increase, so the graph only remain as a straight line governing the Ohm's law. Here the graph will be a bit different, and you see both the graphs are side by side here. You can understand that we have to calculate the resistance for this non-ohmic. I repeat, this is called non-ohmic. Why it is called non-ohmic? Because it is not following the Ohm's law. In other ways, practically the temperature of the conductor increases when the current passes through it, and even the other physical properties also somehow changes, and that's why we don't get this straight line. Okay, so this is it regarding the verification of Ohm's law and the ohmic and non-ohmic graphs of V versus I graphs. Those are plotted here. Okay, these are very important. These are graphical interpretations, so it's very important to know how we can actually interpret these kind of data. All right, now I'll move into other topic for the next one, which is coming up. So laws of resistance actually tells us how resistance depends on a lot of other factors involving a conductor. As I told you, in Ohm's law, temperature and other physical properties remaining constant, this phrase was there. So other physical properties remaining constant refers to a lot of things. Temperature we know already, but the other physical properties remaining constant is very important. We have already got this idea, but let us elaborate. Okay, so what is that? You say that the resistance is directly proportional to the length of the conductor. More the length, more will be the resistance, and resistance is inversely proportional to the area of the conductor. That means thicker the wire is lesser the resistance. Thinner the wire, more will be the resistance. Let me tell you one simple thing. You'll see that the appliances at our home which consumes higher amount of electricity or electrical energy, like air conditioner, refrigerator, washing machines, heater, then microwaves, all these things which consumes a high amount of electrical energy. You'll see the wires, the plug-in wires we use for these kind of appliances, they are quite thick because they consume more electrical energy, means they consume more amount of current, and that is the reason why if you want to pass more amount of current through a conductor, it has to be thicker, so because its resistance will be less. Okay, so knowing the consequences, we can now have these expressions together. We can actually bring a constant which is called rho, combining these two, and this symbol rho is a very specific property for a conductor, and it is called resistivity. Okay, this is very interesting fact. The resistivity of a conductor is practically dependent on a lot of factors, but rho is the constant of this kind of expression, and here we can see that rho is defined as the resistivity. The unit you can you directly calculate from here. It's basically ohm meter. Okay, because L is meter, A is meter square, so ultimately it will be ohm meter. All right, so we know what resistivity is, but we have to understand exactly the expression. For L equals to 1 unit and A equals to 1 square unit. I mean, if you imagine a cube, okay, the cube of side 1 unit and the area, area of cross section to be 1 unit. I mean, if everything is 1, say 1 meter, then this area is definitely 1 square meter. And if you assume that the current is flowing like this, I mean, from it is entering through this space and going out from there. So what you can see is that if everything is 1, this is 1, the area is of cross section for these faces is 1, then everything it becomes 1, then R is equal to rho. So resistivity is defined as the amount of resistance where of a conductor having unit length and unit cross sectional area. This is the definition of resistivity. Resistivity is defined as the resistance of a conductor having unit length and unit cross sectional area, or we can imagine a cube having unit length and then the resistance between two opposite faces of that cube is also known as resistivity. Okay, so this is the thing, and again we also have another thing called conductivity. Conductivity is the reciprocal of resistivity, and it is 1 by rho, and it is actually ohm per meter. Per ohm per meter is the unit for conductivity, which is reciprocal of resistivity. Now let me tell you a few things which are theoretical, but a lot of question comes for 2 marks, 1 mark and all this. They say that what are the factors on which the resistivity of a conductor depends. Resistivity is a very unique property of the material of the conductor. Okay, the copper, it has got a standard resistivity. Silver, it has got a standard resistivity. Even other materials, other conductors, even the alloys, they have different resistivities, and those are constant. So resistivity depends on a lot of factors. First of all is substance, definitely. The more the substance is a conductor, the resistivity will be lesser, and because you can understand, resistivity will be more, so that it can give you a more conductivity. And the substance which are insulated, they will have a very low resistivity, because it is ultimately give you an expression which is like a lot of it's dependent on the substance of the material through which we have constructed the conductor. Okay, so next is obviously the temperature, and temperature dependency of resistivity is very interesting, because of the one fact I'll show you certain graphs right now in a picture, and you'll see that resistivity varies with temperature in a different manner. For alloys, it has a different behavior. For pure metals, it has different behavior. For semiconductors, it is having a different behavior. So obviously, with respect to temperature, it behaves differently. Only thing on which the resistivity does not depend, I repeat, only thing the resistivity which does not depend is the physical state or the physical dimension of the conductor. That means the length or the area. Resistance is dependent on length or area. Resistivity doesn't. Please remember this. I have seen lot of students do this mistake, that they are asked that how resistivity of a conductor depends on the length. They write the thing what we have learned about resistance. So they mix it up, but don't mix it up. Please try to understand that resistivity is independent of the length or area of cross section or other physical dimension of the conductor. Okay, there will be certain graphs coming up now. Please watch it and understand that how resistivity and even the resistance, that means the potential versus current graph, can vary for different types of substance or different types of sources we are using, and that is very important. Like for bulb we have a different VI graph, and also for resistivity for alloy we have different, we have pure metal we have different, for semiconducting devices like germanium, silicon, we have different graphs. Okay, so you have to understand how these work. Graphs will come up now.
So here we can see the various V versus I curves for different types of conductors, you can see, and hopefully you can understand that all the time the graphs won't be linear like V equals to IR. So it will have curvatures, and that point of time we will be going for the non-ohmic curves that I already have shown you in the class. Okay, so please practice this graph, because they can ask you to draw any one of these graphs in your board exam, so be careful about it. So here is the variation of resistivity with respect to temperature. As you can see in the graph, we have plotted the temperature in Kelvin scale, and the resistivity is in the order of 10 to the power minus 6. Okay, and we have taken an alloy nichrome, and we can see that in case of nichrome the increase in resistivity with respect to the temperature is very is not very sharp. Okay, it's increasing but very gradually, it's not going very fast, unlike conductors where resistivity increases very sharp. But here we can see that nichrome is an alloy, and you should understand, please note it down in your classwork, that alloys have a tendency to show this kind of variation with respect to temperature, that the resistivity of alloy doesn't change much with the change in temperature. Okay, please note it down. Here you can see the change of resistivity with respect to temperature plotted in Kelvin, and the resistivity about the germanium and silicon. And you know that germanium and silicons, they are semiconducting materials. So you can see the resistivity falls very sharp towards almost zero, and that's the reason why semiconductors at low temperatures or at certain temperatures, they work very fast than the normal conductors that we have. Okay, so this is another interesting fact about resistivity that I was telling you, that to know certain things, okay, you have to explore more from your textbook. Okay, keep learning and find out more about resistivity and resistance, and the variation of these quantities with respect to temperature and other physical properties. Okay, so do study the textbook and you'll find out more interesting facts about all these. Okay.
Electrical power, and that is the only way we can actually convert electric energy into other form of energy. And we always try to measure the amount of consumption in the terminology of power. Okay, so this is very important. Let us do that. Now electric power is actually fetched from the concept of work per energy only, that we already know about work per energy. So whatever power we define there, it is the same thing which is there in electricity, only the work done or energy is current, electrical energy. In work per energy we did a lot of things about mechanical energy. Now it is related only to electrical energy. So let's do find out the expression of power. So power is basically work done by time, that we know, right? So work done by time, and work is potential into charge, because definition of potential was work done by amount of charge. So W by Q was V, so VQ is W. Okay. So now what I can see, Q by T is current, that I know. So power here is equal to potential into current. So the unit of power is watt, and in electrical power, and we can say that 1 watt is actually equals to 1 volt into 1 ampere, and this is what we have a basic relationship, but this relationship can be modified. Now how we can modify? First of all, V is equal to IR, that we know from Ohm's law. So power can be also written as I square R, which is mostly used in doing numericals for series combination of resistances that I'll do. These things we use this kind of expression. And also I is equal to V by R, so power can also be written as V square by R. So this is another expression which is also important for doing the sums based on parallel circuit. We use this form. Okay, so series we use this form, and parallel we use this form. I'm coming to these things. I'll be deriving all this, but right now, just for the sake of information, you remember. So we have already understood what power is, how we can fetch the the simple expression of power. We have a lot of things to do that it will come, but right now it is the fact that power is work done, electrical work done per unit time, and electrical work done is potential into charge, and that way we can actually get power, or 1 watt in electrical terminology. 1 watt is equal to 1 volt into 1 ampere. We definitely have higher units like megawatt, kilowatt. These things are used widely. You find any electrical appliances, you buy anything, even a bulb, you'll see there is something written, and say 10 watt, 11 watt, 20 watt, 30 watt, something is written, and that is the amount of consumption of current electricity that we are doing, and that is the amount of current electrical energy we are actually consuming. That gives us the expression of consumption of electrical energy. Okay, so let us move into the next topic. Hope you have understood this, the electrical power, the basic of electrical power that we have derived here, and now we'll move into the next topic. Let us do a few problems. Okay, so first problem here is written, is based on power. A bulb rated 500 watt and 100 volt is given. A bulb rated 500 watt and 100 volt. If it is connected to 200 volt, what resistance should be used in series? This is the question they have asked. So we have a bulb having a power of 500 watt, and it is operating potentially is 100 volt. Okay, that's why we need to have another resistance in series so that we can be operated at 200 volt. So the supply is 200, but the amount of consumption or the amount of potential drop across the bulb will be 100. Another 100 will be in the other resistance in series, because in series only we can have potentials to be added up. Okay, so let us calculate the resistance of the bulb, which is the power equals to V square by R. So here V square by P, that means 100 square by power, will give me the resistance, which is 100 into 100 by 500, and that is effectively is 20 ohm. So 20 ohm is the resistance of the bulb. Okay, so now we are having this operating potential is 200 volt, and we have to add some resistance in series. Okay, fine enough. So in this aspect, what we can find out the current also. Current is powered by potential, and it is 500 by 100. This is for the bulb I am talking about, is 5 ampere. So bulb can consume up to a current of 5 ampere. Above that, the bulb will not work. Okay, the filament will break, or some heating element. So due to the heating element, the filament will break or something, the bulb will get fused. So 5 ampere is the maximum permissible current the bulb can withstand with this operating power of 500 watt in 100 volt. Okay, so 5 ampere. So now we can actually write that 5 ampere. Now the supply potential is 200 volt, and we are using another resistance in series with the bulb, which is 20 ohm is the resistance of the bulb, and another resistance is used, R dash, in series. This is 5 ampere. So finally we can have this R dash plus 20 is equal to 200 by 5, which is 40. So from here we can easily calculate that the series resistance that we have to connect with this particular bulb is 20 ohm in order to make it operative at potential of 200 volt. Okay, so is this sum simple? Okay, these are very pretty sums that comes in board exams for 2 mark or 2 marks or 1 mark question. These are not so difficult. We'll do sums later on where we'll require more principles and laws to follow. But right now, the topics that we have covered in this first part, these are the kind of sums that even it comes in board. So we have to practice this. Okay, so let's come to the second problem, and here it is a problem based on resistivity. So let's check it out. It says that a cylindrical wire is stretched by 10%, and we have to calculate the percentage increase or change in resistance. Okay, so since the length is increased, stretched means it is stretched by its length. Okay, so 10% is the new change. So L dash is equal to L plus L by 10. 10% means that. So 11 L by 10 is our new length here. But we have one thing, that when we are stretching a wire, it's cross-sectional area decreases because we are not changing its volume. We are just stretching it, the length increases but the area decreases. So volume remains constant, and if the volume is constant, okay, so what I can say that A1 let's say like that, A into L is the volume, is equal to A dash L dash. Okay, so from here we can actually have a ratio which is A by A dash, and that is L dash by L, and you can see L dash by L will be 11 by 10 only. Okay, so this we have. Now we have to know the percentage increase in resistance. So here I can say R dash is equal to rho is constant, because resistivity does not change with the increase in length, or even increase in area or anything. It does not depend on the physical change in physical dimension. So R dash equals to this, and R equals to this. So we can write that R dash by R, we can directly calculate, it is L dash by L into A by A dash. L dash by L is 11 by 10, and A by A dash is 11 by 10. So it is 121 by 100 is the thing. So R dash is 121 by 100 into R, and from here they have asked us to change the percentage increase. So we can see it is increased. So now we have to just do one thing, that we have to find the change. Del R is equal to R dash minus R, which you can eventually understand is basically 21 by 100 R. So percentage change you can easily now calculate, that is del R by R into 100, which is 21%, as you can see here. 21 by 100 R into 100 will definitely give me 21%. So here is another problem based on resistivity, based on the laws of resistance, the length and other things, how it changes. So you have understood that how we can approach to these kind of problems, and these are pretty simple problems that come for 1 mark or 2 marks question in board exam. Alright, so hope you have understood. Now let us check for the next topic right now. So now we'll be doing a concept called internal resistance. You know already that the EMF marked in the cell and the potential obtained within the circuit, they are different. Obviously they are different, always we find it that way. So we have to somehow account this difference. Okay, there is some amount of potential of the energy is lost, and this energy is lost within this battery or the cell or during the conversion of chemical energy into electrical energy during that time only. Alright, so here we have to understand that the potential which we are obtaining for this external resistance capital R, which is recorded in the voltmeter, which is always connected in parallel to the equipment, and also the current which is flowing through the circuit we can calculate in the ammeter, which is connected in series in the circuit. And we have the cell which is having an EMF E, and already suppose we are thinking that there is some amount of lost volt. Now what is the lost volt? The lost volt is basically this, the total marked minus total obtained, and that is the amount of loss that we are incurring. Okay, so this is the thing, and then we thought, okay fine, since there is a loss and we cannot actually account for it, so we thought that within the cell or within the battery itself there is a resistance which is actually consuming this amount of potential which is lost. Okay, and after this loss only we are getting the current or we are getting the potential within the circuit. So within the battery, within the cell, this internal resistance is creating or causing this loss to occur. So we can say that E minus V is small I into small r, which is termed as internal resistance. Okay, so this is now we have an expression. Now what we can do is very simple, that we can divide the whole thing into this form, that is by capital V, and you know that capital V is equal to basically I into capital R, because this is the potential drop across this resistance. It is connected in parallel across this resistance. So potential that what we are obtaining in the circuit is V, and that is equal to small I into capital R. Okay, so from here we can easily calculate the value of small r, which is capital R into E V minus 1. You see, we have a simplified expression in order to calculate the internal resistance of this particular circuit, or this particular cell using this circuit, and we have this expression small r equals to capital R into E by V minus 1, and this E is the EMF marked in the cell and V is the potential retrieved within the connected circuit. Alright, do remember this expression. This is very important. It will be used a lot of times, even in the latter part of current electricity. You will see that this part is used lot during doing the numericals and other things. Okay, so hope this you have understood, that we have understood the concept of internal resistance, we have understood the concept of EMF properly. Now that we have understood why this loss occurs and how we can account for this loss, and that is the reason why we have brought this concept in current electricity called internal resistance. So now we are going to learn a very interesting topic for current electricity, which is the combination of resistances. You see, we don't use a single resistance or at the real practice. We use a lot of resistances together, and that's the reason why we should know that what is the effect of combining a lot of different resistance together and what does it give us. And for that reason, we'll be knowing this thing, the combination of resistance, and also you should know that there are two different types of combination. One is called series combination, that is Series means one after another. The way you visualize series combination is that one resistance will be followed by another, will be followed by another, and so on and so forth. So let us draw such arrangement. You know the resistances are like this. So let us take three resistances R1, R2, and R3, and we are passing current through it. And individual resistances, they will develop individual potential drops, because for each of these three different resistances we have different potential drops occurring at individual resistances. But remember one thing, that current remains constant here. Current remain constant. Okay, this is the main logic behind series resistance, and that is that the current will remain constant. So total potential, if it is total is V, then we can say that these are the sum of all these three different potential drops. And so V is equal to I into R equivalent, that is the equivalent resistance I am going to obtain out of all these three resistances we are using here. And I V1 will be equals to I R1, this is I R2, and this is I R3. So effectively we are getting an expression which is like this. So equivalent resistance in series combination is the sum of all the resistances thus connected, and it is just R1, R2, R3 addition. So you can understand, in series combination the effective resistance of the circuit increases, so effective current gets decreased. Okay, so this is one type of combination that we have for the combination of resistance. Next we are going to go for the parallel combination. Before going to parallel, I must again repeat certain things. In series combination, remember one thing, that the current remain constant throughout all these resistances. The same current will flow. Okay, and the second part is that individual resistance will occur the individual potential drops. Added them, you will get the total potential of the given circuit, that is V equals to sum of all these three potentials. Okay, now I hope you have understood. Now let us move into the parallel combination of resistance, which is more interesting. Okay, now let us go for the parallel combination. We are going to do this right now. Okay, please do copy these diagrams and all these circuit diagrams in your classwork, so that for the future reference you can have this in your classwork, so that you can revise it very easily. Okay, so we have taken three resistances in parallel. Parallel means there will be a single branch, and then the resistances will be connected, and then the branch will be closed, and it will go towards the main circuit or the source supply, whatever. So let us take, this is R1, this is R2, and this is R3. If the main current coming to this circuit is I, then what happens here, the current is actually, it gets divided into three parts, and finally it again combines up to get the main current I. And even another point is that suppose if these two are the junctions A and B, where the resistances are diverged, then the potential between A and B will remain constant. So VAB is constant. Unlike the current was constant, here current is getting divided, and potential was here, it was individually different. Now here all these resistances will have the same potential. Okay, so what I can write here, that I is equal to the main current is sum of all these three currents according to the law of conservation of energy. Current is a form of energy, so whatever current it was coming to the junction, the same current will get divided into the three parts towards individual three resistances. Okay, so I is equal to I1 plus I2 plus I3, and I is equal to, you can say the potential is constant VAB. We can write VAB by R equivalent, and that is equal to VAB by R1, and that is equal to VAB by R2, and I3 is equal to VAB by R3. So effectively I am obtaining an expression for the parallel combination of resistances, which is equal to 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And here, interestingly, that in parallel combination the resistance was getting magnified, but in this case the effective resistance is lesser than the least resistance connected. Please write down this particular line. I am repeating, let the in parallel combination of resistance, in parallel combination of resistance, the effective resistance is lesser than the least resistance connected in the circuit. Okay, so it is the least resistance effectively in parallel combination. You can understand, unlike series combination, the effective resistance decreases, so the effective current towards the circuit it increases, and the same potential is applied towards each of all these resistances, which is equal to VAB here. You can see in this particular diagram. So you can understand, in household circuit we prefer to use parallel because all the appliances is manufactured at a particular standard potential that that we use in excuse me, in domestic circuit, which is 220 volt. For in our country it is 220 volt 50 hertz AC, but still in AC also the potential will remain constant in parallel combination, and we use in household circuit we always connect everything with respect to the parallel combination. Okay, series combination has also got a lot of things. We'll come to know about all this later on.